And hope these three instructions has completed. Yes. Further, what about clear? Yes, what about clear instructions? Yes. Clear as completed. Harshavardhan. Harshavardhan. Yes, Harshavardhan present. Shiv Prasad.
Yes, sir.
So, did Madam completed a clear instructions CLR?
Sir, ma'am completed till complement this and no, and or XOR and complement.
Complement. Okay.
Yes,
So
sir.
one more instruction is remaining here. That is clear. Yes. So we have clear instruction as a CLR. Now here we can perform two operations with respect to clear instruction. One is clear accumulator is a one instruction, and clear bit. Clear bit. Now what is this clear instruction? So clear is an instruction which clears the content of accumulator. So accumulator content would be reset to 0. All bits of accumulator would be reset to 0. If you are using clear instruction as clear A, the content of accumulator will be cleared. Now, one more instruction we have, that is clear bit. Now, clear A is an 8-bit instruction, so it is a byte instruction. Clear A is a byte instruction. The clear bit is a bit instruction. So it's a bit manipulation instruction where a single bit will be cleared. For example, we can represent bit here, only bit. For example, if you want to clear a particular bit in a bit addressable area, that will be cleared here. So we can clear the carry. Carry is a bit. We can clear the carry flag. We can clear the addresses from 00 to 7F of the bit addresses So we have a bit addressable area, right? So this is the bit address, not a byte address. So it should be clear for you. So it is a bit address, not a byte address. So byte address also we have 00 to 7F of the internal RAM, and this is the bit address. Is bit address of the bit addressable location. So what is the address starting for bit address? This bit addressable location. What is the address starting for the bit address? The byte address of the bit addressable location starting from what? Hope all of you getting this? Is what is the address? The address area from 20H2 what? 20H2
2FH.
is 20H2 2FH. So 30. So total locations from the bit addresses from 00 to 7F would be a 128 bits. Is ranging from the location 20H2 to FH is the bit addressable area. So we can represent any of the bits. So we can clear the carry flag. We can clear a single bit. Whatever address you are going to represent here, the bit of that particular will be clear. For example, if you write CLRC, means carry flag will be made equal to 0. Yes. So it's an example. If you want to clear CLR, a particular bit of the bit addressable location as 0, 7, and that particular bit will be cleared. So 0, 7 will be made equal to 0, and so on. We can use a bit address. So this is about the clear instruction. Clear instruction. So clear instruction can be represented as the bit addressable instruction or a byte addressable instruction. Only two instructions are possible here. Only two instructions are possible. Either it is clear A or clear bit. No other instruction can be written in the clear using a clear instruction. We cannot write in a different addressing mode also. Yes, only these two instructions are possible. Yes, hope all of you got this. So further, a few logical instructions as the rotate and swap. Rotate and swap instructions. Now, what do you mean by rotate operation? So, rotate operation is nothing but if you have 8 bits here, we can rotate the content of this 8 bits. Means we can make this LSB content and MSB content to shift their positions. Now the content from 0th bit, will be shifted to 7th bit, from 7th to 8, 6, 6 to 5, 5 to 4, then 4 to 3, 3 to 2, 2 to 1, and 1 to 0. Individual bits will be shifted. Yes, so this is a rotate. It is a rotate. So further, if you execute a one instruction, so one position will be shifted. Yes, so it is a rotate operation. It's a rotate. Continuously, we can rotate the contents of these bits. Means from the 7th to 6, 6 to 5, 5 to 4, and so on from 0 to again to 7. Yes, so this is a rotate operation. So we can perform the rotate operation in 4 different ways. We can perform in 4 different ways. Either we can perform rotate right, rotate left. These are the 2 operations. Further, we can rotate along with the carry also. We can rotate along with the carry. We can perform rotate left with the carry, rotate right with carry. So these are the 4 operations we can perform. Yes, either we can rotate a simple rotate without carry, or we can perform the rotate left or rotate right without carry, as well as rotate left and rotate right with carry. We have 4 different instructions for the rotate operation. That is rotate left or rotate right without carry can be performed as a byte instructions. Can be performed as a byte, and also rotate left, rotate right with carry can also be performed as a byte, but it involves, apart from these 8 bits, it involves one more bit, that is a carry bit. It also involves the carry bit. Yes. So for example, we'll start with the rotate left. Now the rotate left can be performed the content to rotate from right to left. It performs the operation from right to left. For example, for all the rotate operations, so rotate left can be represented as RL, rotate left. For all the rotate operations, it is only possible to perform with the accumulator. Rotate operations can only perform with the accumulator itself. Yes, rotate left will perform to rotate from right to left. So 0th bit will be 0th bit will be shifted to one position. Then first bit will be shifted to second position, that is a bit 1 to bit 2, from bit 2 to 3, 3 to 4, 4 to 5, 5 to 6 and 6 to 7, and the 7th bit position is shifted to the least significant bit, that is a 0. Yes, this is rotate left. The bits will be shifted from left to that is right to left, right to left. So we can perform rotate left accumulator. So we don't have any other instructions. We have only rotate left accumulator. The content of accumulator can be rotated. No other register will be used to rotate operation. So only accumulator is used. We have only this instruction. We don't have any other instruction, and we cannot write into a different addressing mode. Only we can write into a this. So we have rotate left accumulator. We have rotate left accumulator. Similarly, we can write rotate left RLC. That is rotate left with carry. Rotate left with carry. So carry is also included along with the accumulator. Carry is also included along with the accumulator. The content of the accumulator will be along with the along with the content of the accumulator. The carry can also be rotated. So we have a rotate left with carry. Rotate left with carry. Now the carry bit is also included in the rotate operation. The content of 7th bit is loaded into the carry flag, and further carry flag will be loaded into the least significant bit. So this is rotate left with carry. Without carry, simply 7th bit will be loaded into the 0th position. Yes, so that is simple rotate left. Now the content of if you are using RLC, that is rotate left with carry, the accumulator, same operation as the rotate left is performed, but 7th bit position will be loaded into the carry flag. That is MSB position will be loaded into the carry flag. Further, the content of the carry will be loaded to the 0th bit position. So one more bit is been involved here. So here it remains MSB position. Yes, and further the carry content will be placed into the 0th bit position. In earlier case, only with the rotate left, the MSB will be loaded into the LSB. That was a simple rotate. So here rotate with carry would include the carry content also. So this is the rotate operations. So we have two operations in rotate. So further, that is the RL and RLC. Only the content of accumulator can be rotated. So all of you got this. Further, we have two more instructions as rotate right, represented as RR, the content of accumulator. We can only rotate the content of accumulator to the right side. So the content will be moved from left to right here. Similarly, how we have represented, we can represent the rotate right, so rotate right would perform the content to move from left to right. The content will move from left to right. The 7th bit position will be moved to 6, 6 to 5, 5 to 4, and so on, from first position to the 0th, and from the 0th position to the 7th bit. From 0th position to the 7th bit. The content of 0th position will be moved to 7th bit position. So this is rotate right, and in this case also we can involve rotate right with carry. Rotate right with carry. So all of you understood what is rotate right? Rotate right is opposite to the rotate left. The instruction used as the RR, rotate right, and one more operation we can perform, that is rotate right with carry, RRC space A. RRC space A, rotate right with carry. Same representation we can make with respect to rotate right. Hence, the carry content, the content of the carry will be loaded into the 7th bit position here, and so on the content will be shifted. Further, this content of least significant bit, that is 0 bit, will be loaded to the carry. Yes. So it is rotate right with carry. So in opposite to the rotate operation, that is the rotate left operation. In contrast, we can represent rotate right and rotate right with the carry. Hope all of you got this rotate operations. One thing you need to remember, that we can only perform the rotate operation with the accumulator, not with any other resistor. We can only perform with the accumulator, not with any other resistor. And these are the 4 instructions used for rotate. Yes, hope all of you got this. Any doubts in rotate operation? Simply a position bit position will be changed. Bit position will be changed. Now, can you perform one operation for rotate left? RRA. Perform RRA for the bits accumulator containing as 0, 0, 1, 1, 1, 1, 0, 0. So perform this operation twice. If you want to perform this operation twice, we need to write the 2 instructions. So in each instruction, in each execution of that instruction, would rotate 1 bit position. The content will be rotated 1 bit position for every instruction executed. Now, what happens if you execute twice? So place the content. What would be the content if you execute twice here? In first execution, the content of accumulator will be, it's a rotate right, that is the content from left to right, hence 0, 0. This 0 will be loaded to the MSB position. This will be shifted. This will be shifted. And this bit is shifted. Further, this bit is shifted here. Yes, and so on. This is the first rotate. And for second rotate, the content of accumulator would be again loaded with the least significant bit, that is 0th bit to 7th bit. 0 will be again loaded to the 7th bit. Now again this 0 is shifted here, this 0 and again 0, and further 1, 1, 1, and all of you got this. So earlier it was, the data was the data was 3 is 3C, and now it is 0F. So if you rotate data to C 2 times, rotate left, then it will be converted into 0F. All of you got this? So this is how we can perform the rotate operation. So how many bits you want to shift? So you can simply execute the rotate right or rotate left operations according to your application, that many times it would be shifted. Hope all of you got this. Now, try one more example. That perform now you can perform one more example with respect to rotate left the content of accumulator, assuming the content of accumulator as assume the content of accumulator as this and perform rotate left 4 times. Perform rotate left 4 times and represent the content.
F0, sir.
Yes, you would got F0. We would got F0. After 4 execution, it is 1 1 1 1 0 0 0 0. Yes, every time each bit will be shifted, and after 4 execution, it would result into completely the lower nibble will be placed at the higher nibble, and higher nibble will be placed at the lower nibble. If you perform rotate left or rotate right 4 times, the resultant would be the same. Either you can perform rotate left or rotate right. If it is performed the 4 times, the resultant would be same. If and go through the previous clear instruction. Go through the previous clear instruction. Did we complete? Yes, we have completed clear instruction. Yes. So what instruction you have taken that? Whether CRL or CLR?
CLR.
CLR. Okay, fine. Yes. Next. So now, by this example, what we can say, if you want to swap the content from higher to lower nibble, we need to use rotate left or rotate right 4 times. Is it? Now, instead of that, we have a specific instruction as swap. We have a specific instruction as a swap. Swap A. What it will do? It will swap the content of the lower and higher nibbles. It will swap the content of higher and lower nibbles here. Means instead of using rotate left or rotate right 4 times, if you are using swap A, the content of higher and lower nibbles of the accumulator will be swapped. Yes. For example, this is the only one instruction we have for swapping the lower and higher nibbles. So what happens? The lower 4 bits and higher upper 4 bits 0 to 3 and 4 to 7. So we have a lower nibbles. So this is higher nibble. Lower nibble. So this will be swapped. The content of this will be swapped. Higher and lower nibble will be swapped. Yes. for example, if assuming the content of accumulator with 0f, assuming the content of accumulator with 0f, after execution of this instruction, it will become f0. Otherwise, what we need to do, we need to use the rotate right or rotate left instructions 4 times. We need to use rotate left and rotate right instruction 4 times. The resultant will be same, but instead of using 4 times, you can use the swap instruction, which will immediately within a execution, that is a within by using only one instruction, so we can swap the content of lower and higher nibbles, and we can arrange into a swapping of the content of accumulator instead of using 4 instructions. Yes, so this is the only one instruction we have. This is the only one instruction we have to perform the swap instruction. That is to perform the swapping of the accumulator of lower and higher nibbles. Couple of you got this. So these are the instructions what we have in the logical instructions. Swap A. First is a AND instruction, OR, XOR, complement, clear, rotate. We have rotate right, left, with carry and without carry, and we have a swap instructions. Yes, so these are the instructions in logical operations and instructions we have. So all of you got this. We'll go through these instructions with an example. Yes, do you have any doubts in these instructions? No doubts. Yes, fine. Next, we'll move on to the data transfer instruction. So these instructions are important in 8051 because whatever operation we are going to follow, we are going to use the data transfer instruction itself. If you want to move, store, load, these instructions are used extensively in 8051. In say in most of the programs, we are going to use the data transfer instruction. The data transfer instruction includes only one instruction as a move, MOV. So we can write it as MOV, destination byte comma source byte. Destination byte comma source byte. Data transfer instruction, and the syntax of data transfer instruction is move, destination comma source, destination byte comma source byte. Here we are going to perform 8-bit operations with respect to destination and source. Destination and source. Now we can write these the move instruction in different ways. Means we can transfer data in different way. We can transfer the data in different way. The first condition we'll consider as the accumulator as the destination. Accumulator as the destination. Now write the instruction by considering the accumulator as the destination here. Consider accumulator as the destination and represent the instructions. Accumulator as destination means move A can be represented and source byte can be anything here. Source byte can be any addressing mode. Yes. So move A using the accumulator as a destination. So A is the destination here, and accumulate and further any source byte, any addressing of the source byte. So it might be immediate addressing. Yes. So this is the one option, one possibility. Next, move A. We can have the resistor as the destination, source, and move A. We can have the direct address as the source, and also we can have indirect address. Yes. So these are the four different ways we can represent by considering the accumulator as the destination. Hope all of you are getting this. Yes. So these are the four possibilities of representing the move instruction when accumulator is the destination. Accumulator is the destination. Hope all of you are getting this. Clear with this? The general syntax, what we can represent? We can represent the general syntax as move destination comma source. Yes, move destination comma source. But we don't know what would be the destination and what would be the source. Hence, we are considering the different possibilities. First, considering accumulator as the destination, then source might be any of the addressing modes. Source might be any of the addressing modes. Got it? And if that is the case, we can write move A with the immediate addressing, move A with the register addressing, move A with direct addressing, and move A with indirect addressing. So these are the four possibilities what we can get when accumulator is considered as the destination. Next possibility is that register A as source. Register A as source. When you consider register A as source, in what different way we can represent? Think about immediate addressing. Can we represent immediate address in a destination position? Source will be accumulator, it's a fixed. Source will be accumulator, which will be the fixed one. That is comma A is a fixed one. Now, so destination might be any of the addressing. Destination might be any of the addressing. We cannot think immediate address as the destination here because it is invalid. So we cannot represent that. We can have Rn, the register as the any of the bank register as the destination. That is fine. Next possibility is that move A is a common because we have considered A as a source. Now direct address might be any of the possibility. We can write the direct address might be a destination. Then move indirect might be any. It might be destination. Yes. So these are the three possibilities what we can represent when we consider register A as the source. Register A as the source. Hope all of you are getting this. Any confusion representing these instructions? Anybody facing any difficulty representing these instructions? Go through this these two possibilities of representing source and destination, considering accumulator as a source and accumulator as the destination. Hope all of you understood. If you understood, we'll move to the next consideration.
Sir, immediate addressing mode, it's not possible. Yes, sir.
It's not possible because what is immediate addressing mode? The immediate value to be moved to one location. I want to move the content that is immediate value. Now
Yes.
we have the syntax as move destination comma source. Hence we cannot change the syntax. Destination comma source positions will be fixed. Yes, first will come the destination and then come the source. Always we know that the content from source will move to destination. Is it? The content from source will be moved to destination. We
Yes.
cannot move the content from destinations to source. Yes, in 8051, this is the execution happens. That means the source content will be moved to destination. This is the execution. We destination content will not be moved to source. In all the instructions, this is the execution happens. The source content will be moved to destination and it will be placed in the destination. In arithmetic, in logical, whatever operations you are going to take, always this operation happens. The content of source will be moved to destination, means whatever operation, add operation, same thing happens. The content of source will be added with the destination and placed in a destination itself. Yes?
Okay.
Hence,
Okay.
this is a fixed. Now, when we consider a immediate number as the source, that will be moved to accumulator. But if you consider this immediate number as the destination, it doesn't have any meaning because the content of an accumulator is not placed onto the immediate value, is it? So that in that case that will be invalid. So always in immediate addressing mode, the immediate value will come under source. It will not come under the destination. It is not possible. Hence we cannot represent that immediate number into this location.
Destination.
Yes, so all of you got this. Only these are the three possibilities ways of representing when A is considered as source. Yes, further the third possibility is that we can consider a resistor or Rn as the destination. Resistor Rn as the destination. What is Rn? Rn might be 0 to 7. It might be 0 resistor 0 or resistor 1 2 till 7. In general, we can represent it as Rn. If you consider Rr, you can interchange. In some of the textbook they have represented Ri or whatever it is. So simple representation that whenever you get the at symbol here, it is 0 or 1. If you write apart from that any labeling, that might be 0 to 7. You don't have a specific representation for the general resistor to R0 to R7. Yes. Now we consider that Rn as the destination. What are the different possibilities we have, or we can represent Rn as the destination? So think about these. Means move is fixed here, move Rn is fixed. Now source might be any of the addressings. This is fixed. Move Rn. Now what might be the source? Source might be immediate value. Yes, source might be immediate value, and source might be what we can write here. Source might be, think about it. We can write source might be accumulator. Yes, source might be accumulator or move Rn comma. It might be address, that is a direct address, and it cannot be immediate. It cannot be indirect. It cannot be indirect. Hope all of you got this. But here, if you observe, already we have represented this instruction. Yes, it's been repeated here. So you can rule out. You can rule out this because already it's been represented under this condition. Yes. Now further, considering direct address as the destination. Now go through the different possibilities of representation of direct address as the destination. The fixed instruction will be move address. Yes, the first possibility is that it can be of immediate value, it can be accumulator, it can be any resistor. Yes, then it can be indirect, further it can be address 1 comma address 2, that is we can move from content, that is a direct address 1 to direct address 2 means representing in that way. We cannot write it as a direct 1 or 2. Here we have to write the address from one direct address to other direct address. We can perform the move operation. Yes, so these are the different possibilities of using the direct address as the destination. And if you observe, this instruction is repeated here. So you can rule out that instruction because under register A as the source, we have already represented that. So you can rule out this instruction. Any other instruction repeated here? No. Yes, no other instruction is repeated. So we can represent in 4 different ways when you are using the direct address as the destination. Yes, and if you are using the direct address as the source, we can represent in either way. So that will be repeated further. So we are not going to consider that. And next 5th representation would be indirect as source, destination. Indirect as the destination. So what we can write for indirect as destination? So fixed would be move at or r, move at or r would be fixed here. We can write this fixed, but source might be accumulator. It is a one possibility. Yes, and we can write any immediate number, or we can write any direct address. Any direct address. So we cannot write any resistor there. We can write it as the direct address. So this is the possibility of representing when indirect resistor is used as the destination. So if you observe here, do we have repeated any instruction? Yes. So this is repeated, so you can rule out this. And any other representation? No. we cannot, we don't have to represent in any other way. No repetition we have read here. Yes, hope all of you got this. So these are the different possibilities of using move instructions under destinations and under source. So collectively go through the instructions and how many instructions you can find. How many instructions we can write in move?
15.
Yes, we can write 15 instructions. Hope all of you got this. Because we have repeated some of the instructions, so we need to roll out this, and roll out this. So we have these 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, 15. In 15 different ways we can write the move instruction. Hope all of you got this. In 15 different ways we can write the move instruction. But along with these data transfer, we have one more, few more representation of the move. Can you quote any of the example for that? Apart from 15 instruction, we can use the move instruction in different way also. I mean, by using a different representation of the move with 16-bit representation. That is, along with this, hope all of you understood this. Along with this, we can write the move as with the 16-bit value. Move dptr, comma 16-bit number. We can write the 16-bit number. So immediate 16-bit number can be moved to dptr. And one more instruction we have, two more instruction we have. What is that instruction? Specific instruction here. Whenever you are using the external memory as move x, we have move x, that is move x a comma at dptr. This is the fixed instruction. Further move x at dptr comma a. This is also fixed. These two are fixed instructions. What we have is, and two more instructions we have as a move c a comma is a comma at a plus program counter, and move c a comma at a plus dptr, a plus dptr. Yes. So these are the specific instructions apart from the 15 instructions what we have. Yes. So specifically when we are using the external memory, this instruction is used, and as a move c, move x. So these all comes under what addressing mode? Indexed addressing. This all comes under indexed addressing. We are not using them frequently. Rarely we are going to use them, but move x we are going to use little frequently compared to move c. Move c is being rarely used. Move c is being rarely used because we don't have any specific reason to access the coded space until or unless you have any written space into a code space as the lookup tables or any data to be retrieved, or any notable data, or any data which has been extracted from the so say reading of the temperature, reading of any specific values indicating a particular value with respect to a resistance. Yes, so that can be written as the lookup table into the move space. Hence, if you want to access that, we can use the move C instruction to access that particular content, or some message you want to extract from the code space, that can be done by the move C. So very rarely we are going to use move C instruction. All of you got this? So these are the 15 instructions. Along with 15, we have move dptr with 16-bit value, move x, and move c instructions. So hence, these are called as the data transfer instructions. These are called as the data transfer instructions. Yes. So I'll wind up for today's class. And in this class, we have discussed about logical instructions as complement, clear, and rotate swap instructions, rotate and swap instructions, and we have discussed data transfer instructions. So you need to note down these instructions, and these everybody has to represent without saying these instructions. You should be able to write these instructions, because in many of the programs, in all the programs, we are going to use the data transfer instructions extensively. Yes, the operation would be less, but the data transfer instruction would be more, because we want to access the internal RAM, we want to store onto the internal RAM, if we want to access the external RAM, internal RAM, it is being done by the move instruction itself. Yes, so these we can call it as the basics of all the instructions. Yes, primary, or we can say primary instruction. So I'll wind up the class for now. You can take a screenshot of this instructions and practice them. In the next class, we'll discuss about a few more instructions as exchange, push and pop instructions, some specific instructions we will discuss, and also branch instructions we are going to discuss. Branch, call and subrouting instructions, and so on. Yes, if you have any doubts, you can list your doubts by the next class, so you can clarify your doubts. Yes, I'll wind up the class for now, and next class will be continued. Bye.